Yeah, we'll continue our discussion here. So in the last class we have discussed about heat of reaction, okay, numericals based on that, okay, and now here we'll be discussing enthalpy of combustion. So enthalpy of combustion means like it is nothing but a oxidation only, okay. So now say methane undergoing combustion, it means methane we are treating with oxygen, okay, with the supply of oxygen, methane undergoing combustion to form CO2 plus H2O, okay. The amount of heat released when 1 mole of a substance is completely oxidized. So what is the substance, like how much amount? 1 mole of a substance, it should be undergo complete oxidation. So that process we can say that one as a enthalpy of combustion, okay. So now enthalpy of combustion of methane, delta Hc of methane is how much they mentioned? So during the combustion of 1 mole of this methane, 1 mole of methane is nothing but how many grams it is? 1 mole of methane means 16 grams. 1 mole of methane corresponds to how many grams? 16 grams. So 16 grams upon combustion we are going to get how much heat? 890.3 kilojoules of heat is released when 16 grams or 1 mole of methane combustion gives 890.3 kilojoules of heat, okay. So I am writing here 890.3 kilojoules of kilojoule per mole it is written. It means per mole of this substance we are getting this much amount of heat, okay. So now there is a term called calorific value. What I am saying? Calorific value. So this calorific value is used to determine or to identify the efficient fuel in the given different fuels. For example, we can use methane as a fuel, ethane as a fuel, and hydrogen gas also as a fuel. So each of these compound upon combustion gives some specific amount of heat, right now? That is what its heat of combustion. Now heat of combustion of methane is how much we got? 890, okay. Now heat of combustion of hydrogen we have. Hydrogen is around minus 69.5. This is an approximate value, okay. So this value is in kilocalories. I can take here kilocalorie per mole, okay. And I just wanted to convert this into kilocalorie, or I have value also. Just give me some time here. Somewhere in a question I have. Yeah, it is around 210, okay. So in kilocalories how much it is? Delta Hc of methane minus 210.8, okay. So this is in kilocalorie per mole, this is in joules, this is in calorie. Now out of these two fuels, it means in fuel methane and hydrogen, which is efficient fuel, which is having more calorific value, that will be considered as more efficient fuel. So what to do? How can we calculate this calorific value? So calorific value CV, I am saying calorific value of this particular substance is equals to heat of combustion of that substance divided by its molar mass, okay. So now what is the units for heat of combustion? We have either kilocalories or kilojoules, okay. I am taking here kilocalorie just for expression per mole. Calorie, like heat of combustion will be given as kilocalorie per mole. And what about molar mass unit? This is gram per mole. Molar mass means what is it? Gram per mole. For example, for methane, what is the molar mass? 16 grams per mole. If I take 1 mole of methane, it will be having 16 grams as a weight. So I can take like this. So now unit of calorific value is what? Kilocalorie per gram or kilojoule per gram. We can write it like this. Now tell me, what is the calorific value of hydrogen we get? CV of H2. If you want to calculate, you can say minus 69.5 by molar mass of hydrogen. How much? 2 gram per mole. Okay, and here this is in kilocalorie per mole. So now tell me what is the answer here. So this will be around 34.75, okay. So 34.75 kilocalorie per gram, okay. So now what about this the heat of combustion, or I mean say I can say calorific value of methane is how much? Minus 210.8 by 16. So how much it will be? Around some 13. Okay, so 13.1 around. So this is kilocalorie per mole. So which is having more calorific value?
Sir, in grams or kilocalorie?
Kilocalorie per gram. Kilocalorie per gram. So which is having more calorific value here?
13.
So here it is 34, that is 39. So both of them are having minus sign. Na? Okay, so which is having?
13.1.
Yeah, see, whenever we are calculating calorific value, just consider their magnitudes. Like here you can just take like this. Okay, okay, so which is having more calorific value? 34.75 means hydrogen. Whatever may be the heat of combustion, just calorific value means divided with its molar mass. So greater the calorific value, greater is the efficiency of that fuel. Okay, so now let us interlink this to our daily life application also. Nowadays if you observe, if any cars, bikes, if you observe, it is mentioned as E20 on the fuel tank. Okay, so now the new fuel, like whatever the fuel we are using, for example petrol we are using, now it is becoming E20 petrol. So E20 petrol means they will mix. Previously they have considered only petrol, pure petrol, but now they are mixing petrol with ethanol. E20, it means ethanol 20%. Means 100 ml of petrol previously used. Now instead of using 100 ml of petrol, 80 ml petrol, 20 ml ethanol. Combustion, like considering both, they are taking it as E20 petrol. So now tell me what happens when we are taking like this. So now due to the presence of this mixture, the calorific value of petrol is higher, but calorific, when we compare with the calorific value of ethanol, therefore what happens to the petrol efficiency now? E20 petrol relatively less. So now we can get a lower mileage than the previous case. Okay, so this is how you can consider. But what is the use? What is the main use of taking like this? Just to have more eco-friendly gases. Okay, when we combust, like burn this ethanol, we'll get CO2 plus H2. Okay, but when we combust, like when we burn the petrol, we'll get more carbon content is there in the petrol. Therefore, we'll get CO2, H2O. Along with this, some harmful gases like carbon monoxide may also release. So just to decrease this pollution, they are prioritizing ethanol petrol, like E20 petrol. Okay, you can remember like this. Okay, so this is what present topic in the trending. Okay, next we can go with other discussions here. Enthalpy of hydration. So it means what? For a particular salt substance or whatever the substance we have. Okay, when we hydrate this, the energy released or observed when 1 mole of anhydrous or partially hydrated salt undergoes hydration. It means for this CuSO4 we are adding some water here. Okay, so to form its hydrated compound. So during this process, energy released is called hydration energy. Okay, next, enthalpy of solution means instead of adding that particular amount, previously how much you have seen, 5 H2O molecules you have seen, but if we add excess amount, large amount of water or large amount of solvent, so it will be becoming solution of that particular substance. Like KCl, adding large amount of water, it becomes KCl solution. So enthalpy of solution, we can say whatever the energy released during the process. Okay, when 1 mole of this substance is taken and added large amount of solvent like water, so during this process we will get some energy might be released or observed. So that energy will be called as enthalpy of solution. Okay, next, enthalpy of neutralization means neutralization means nothing but adding salt, like acid plus base. Okay, so we need to take one equivalent of H plus ions and one equivalent of OH minus ion. So what it will form? We will get one equivalent of H2O is formed. Okay, so here neutralization means nothing but like water only formed here, H plus and OH minus. So during this process, what is the amount of heat released? That will be considered as enthalpy of neutralization. So what I have mentioned here, one equivalent. Okay, so now whenever you take one equivalent of acid plus one equivalent of base, that gives one equivalent of water. Okay, this is what neutralization here. So now why I am using equivalent instead of mole here? So sometimes if I use HCl, what is its N factor? It means how many H plus ions comes from this HCl? 1. So here moles and equivalents are equal in the case of monobasic acid, like only one H plus. But if I use sulfuric acid, what about this case? How many H plus ions it can release? So 1 mole of a substance, 1 mole of sulfuric acid can able to release 2. So its equivalent number changes here. So that's why we should take in terms of equivalence. So 1 equivalence of acid plus 1 equivalence of base undergoes neutralization. During this process, heat evolved is called as enthalpy of neutralization. Okay, so now tell me, when do we get more amount of heat? We have different types of acids bases now, like strong acid, weak acid, strong base, weak base. So now tell me, in which case, like I can mix like this or I can mix like this, like different possibilities are there. Okay, so in which case we are going to get high amount of heat?
Strong acid.
So whenever we heat, whenever we combine strong acid plus strong base, during this strong acid strong base neutralization, we are going to get high amount of heat is released. So that is equals to around minus 13.7 kilocalorie. This is the amount of heat released when strong acid plus strong base undergoing neutralization. So now whenever you take strong acid plus weak base or weak acid plus strong base, the heat evolved will be lesser than this. For example, here might be lesser than this means it is minus 13.7 now. Lesser than this means just ignore this negative sign. It will be something like minus 12.7 or minus 10, something like that. So here negative sign indicating what? The amount of heat released. It is something like exothermic process with this much amount of heat released. Okay, so during this process, whenever you take this combination, it might be something around 12.7 kilocalories I am saying. Okay, this is the amount of heat released. So why it is lesser than this? Why lesser amount of energy is released? Because whenever we are taking weak base or a weak acid, see, we know the extent of ionization will be more for strong acids and strong bases. But whenever we have weak bases, that extent of ionization is relatively less. It means when I say weak base, the liberation of OH minus ion is relatively less here. So in order to bring out that, in order to ionize that OH minus ion from weak base, some amount of energy is consumed. So here how much amount of energy is consumed during this process? When I say 12.7, 1 kilocalorie of energy is utilized for ionization of that weak electrolyte, whether maybe weak acid or a weak base. Okay, so now will be maximum in strong base strong acid combination, after that this combination, and last finally is weak acid weak base combination. Okay, next. Okay, next, enthalpy of fusion means, so fusion means conversion of solid into liquid. So when 1 mole of a substance is converted from its solid substance to solid form to liquid form, the enthalpy change will be considered as enthalpy of fusion. So for water, this is the enthalpy of fusion. So now there is one more term called entropy. Okay, so entropy of fusion, if they say, what you should take? So entropy, I will tell you again, we will have a detailed discussion, but the formula you can interlink here itself. So entropy of fuel, so entropy of fuel means, just take enthalpy, entropy of fusion means enthalpy of that fusion by T, temperature. So conversion from solid to liquid, na T, what is that process? Melting, right now. So that melting point of that thing, T melting. Okay, so now if this liquid is converting into gas, what this process we can say? Vaporization. So enthalpy accompanied during this process is called enthalpy of vaporization. So now if I ask for entropy of vaporization, what is your formula? Entropy of vaporization. Delta H vaporization by so what we can say, temperature. What temperature? Liquid to gas. So it is boiling right now. So T boiling. Like this you can take. For example, see, enthalpy of vaporization of water is mentioned this much. So what I can take here, delta S vaporization equals to that 40.79 by T boiling. What is the boiling point of water? 100 degrees now. So now what is the unit here? Kilojoule per mole. So take that in calories. All the time take the temperature in calories. So like 100 degrees is the boiling point of water. So add 270 to this. So just take here 373 Kelvin. Okay, so your answer should be kilojoule per mole per Kelvin in the terms of that thing. Is that clear or not here? Right. Okay. So now here a solid substance converting into liquid, converting into gas. You are saying this as delta H fusion and this is delta H vaporization, and from direct solid to liquid gas sublimation. Okay, I can say delta H sublimation. So delta H sublimation is equals to delta H fusion plus delta H vaporization. You add these two things for delta H vaporization. Okay. Next we have bond dissociation energy. See what exactly bond dissociation energy means. You take 1 mole of any substance. So for example 1 mole of water molecules if I take. So 1 mole of water means it will be having this kind of bonds now, OH. Okay. So now the amount of energy required to break one particular type of bonds. For example, it is dissociating to form H and OH. So one of these bond is getting broken here. So it is forming H and OH. Now again we have one more type here, OH type of bond is there. See now this OH bonds are not same, they are different now, because here it is H2O molecule, this is a OH. So they are different. So now this is having separate value and this is also having different value. So now read this definition. The energy required to break 1 mole of bonds of a particular type in a gaseous molecule. So water should be taken in gaseous, substance should be taken in gaseous state. So now for the first process, like I am saying, delta H1 bond dissociation energy 1. So that is 498 and second one as 430. So now the average bond dissociation energies will be there now. That is called as bond energy. So what is bond energy means? Delta H bond energy I am saying. It means what? Average of bond dissociation energies. Average means here how many you have, how many bonds are there here? 2 bonds, different. So take here whatever the average means, that many observations you take. So you can take, add this 2, divide by 2. That will be your average bond dissociation, like average bond dissociation energy, which we are calling it as bond energies. So bond energy of this water molecule is how much here? 464. Just adding by divided by 2. So just read here, bond energy, bond enthalpy or bond energy is expressed as average bond dissociation energies of various similar bonds. Okay.
Dissociation energy only for gases, no?
We should take that in the gaseous state. Okay. So now for example I have something like AB3 molecule. When it is dissociates, what are the things formed here? We will get A plus 3B. I mean 3B it can form. Okay. It can take in multiple steps. Now during this process, if they ask bond energy or bond enthalpy to calculate, what I can say? So which is undergoing dissociation here? Reactant is undergoing dissociation. So now you should take bond energies of reactants minus, if anything is a bond energy of products. Okay, see delta H of that reaction is called sum of bond energies of reactants minus sum of bond energies of products. So we'll see 1 or 2 questions on this. then that will be more clear. See, bond enthalpy is used to define bond enthalpy change of the reaction. Now tell me, what is a proper demonstration? Like I have reactants converting into products. So what is the formula I should use here? Enthalpy change for the reaction means enthalpy of reactants minus bond enthalpy of products. Okay. So here we have this reaction. Tell me, how can I calculate the value? Just read the question once.
The enthalpy of a reaction gives is of 1482 kg per mole. Dissociation enthalpy CH bond is given.
Yeah. So tell me for this.
CH bond given.
If enthalpy of reaction is given, so it means during the process this much amount of energy is released, or whatever the enthalpy change is this much. Now they are asking the bond enthalpy of CH is also given. See, in the given molecule, what are the type of bonds we have? We have CH bonds and we have Cl bonds. So they have given data about CH. Now they are asking about CCl bond energy. Okay, how can you calculate this? See, when this is undergoing dissociation, we are going to get what we are going to get? C plus 2H plus 2Cl they are saying. It means what are the types here, what are the things happening here? Delta H reaction should be written equal to what? I can write, see, we have two types, like two CH bonds are there. So I can take 2 into CH plus, again Cl's are how many are there? CCl are again 2. So 2 into CCl, and this side everything is atom, so that will be 0. There is nothing undergoing dissociation here. So that's what I am making here 0. Okay. So but what we should take here, minus of this thing, that will be completely 0. Okay. So now what I can say, this one is how much value given? 1482. This is equal, and here 2CH is how much? Plus 2 CCl. Okay, next 1482 minus 9, 8, 30. This will be CCl. So this will be how much? 2, 5, 6 by 2. So this will be the bond enthalpy of CCl. Okay? 6. So we have option 1. Okay, so our option number 1 will be correct for this question. Okay, next. So try this question and tell me. Yeah, I want answer for this. Yeah, so tell me, how can we do this? The values of heat of formation of SO2, SO3 are given. The heat of formation of this reaction they are asking. So delta H reaction, whenever the formations are given, what is forming in the given reaction? Products are forming. So write first products minus reactants. Okay, if formations are given, write forming minus deform. Okay, if combustions are given, which is undergoing combustion? Reactants. So reactants minus products you can take. So here product formations are given, so SO3 is forming. Enthalpy formation of SO3 products minus enthalpy formation of reactants, that is SO2, and like O2 is there. So oxygen is in its standard state now. So for the standard state, its enthalpy of formation or combustion will be 0. Okay, so here SO3 is how much?
SO3 minus 18
SO3 second one minus
198 by 2.2
2 and this one,
minus 398.2
so this will be plus
200.
kilojoules. Okay, so here we have easy only. Next, these two questions you can try. What is the relation between enthalpy and entropy? Enthalpy and entropy, sorry, enthalpy and internal energy. Delta H and delta E.
Greater than
Delta H equals to, I have given you, H equals to E plus PV.
PV.
Okay, so from this derivation of this will becomes delta H equals to delta E, and here if you see some reaction is given, we do not have any values for P and V here. So we can write for ideal gas equation PV equals to nRT. Okay, so now I am doing derivation of this thing. Okay, so it is also becomes delta PV means instead I can write delta nRT. Okay, at a particular temperature, if I consider, see at a particular temperature 298 is mentioned, so N and R and T are constant. So here we can write delta Ng RT, because this is a mole, like what I told here, ideal gas, only this gaseous moles are changing. So what is the delta Ng value here? So delta Ng is gaseous products minus gaseous reactant. Gaseous products are 0, gaseous reactants are here 1. Okay, so 1 0 minus, like products minus reactants means it will be 1. Okay, so delta H equals to delta E plus delta Ng RT. Okay, so delta H equals to delta E minus
1
RT. Okay, so which means which is greater here?
delta
So delta H is equals to delta E minus RT. It means this is smaller than delta E right now. Okay, so if delta E if I want, so what you will make? Delta H plus RT. So which is bigger here? Delta E is bigger. So delta E greater than delta H. So yeah, that's it. Next, this one. Next, this one. Tell me.
Conversion, nothing but reactant minus product. So on the formation is asking carbon monoxide.
Enthalpy of combustion of carbon and carbon monoxides are given. Then the enthalpy of formation of carbon monoxide they are asking. Try it. So carbon, once again,
112 kg per mole.
like this we can write the equation. Okay, so now delta H reaction means what I can make? Delta H reaction equals to what they are giving,
Formation asking.
but given data is combustion they given now, so whatever they given you take that. So combustion, enthalpy of combustion of carbon monoxide, okay, so minus 390, but
Asking reaction also.
delta H reaction you take, so combustion of delta HC, combustion of what? Carbon minus delta HC of,
Carbon monoxide.
okay, so take here
3 minus 2
minus
390
390 minus of minus 278, so it will be minus 112 kilojoules.
is the answer.
Okay, so write these things if you require. So will you do this question? Just read the question once. Did we solve this model? That calorific question. So what to do?
CH4 is better rocket fuel.
So how can we do that?
Delta H of fusion by gram molar mass.
So just take their calorific values are given here. Heat of combustions are given now. So calorific value you should find first. Heat of combustion by its
Molar mass.
molar mass. So one which is having higher value, that will be the best fuel. So calculate that by taking their values by dividing with their molar masses. Okay, you will get some value, that will be your answer. Higher the value, greater will be the efficiency.
CH4.
Okay, next this one.
What is the average person needs 1000 kg per day? Amount of glucose is energy required nearest.
Try that once. Maybe. I mean, glucose means carbohydrate, no? So that comes from. Is that clear?
Yes.
So what to do? Say an average person needs 10,000 kilojoules of energy per day. The amount of glucose needed to meet his energy requirement. See how much amount of energy is required, like how much amount of glucose is, like the amount of glucose needed for to meet his energies. Okay. So now what to do? See, this much amount of energy is required per day for a normal person. So in order to gain this much energy, how much amount of energy he need to consume? Glucose. See, the heat of, see, by combustion of fuel only we are going to get energies now. So what is our fuel here? Glucose. So enthalpy of glucose is given here, combustion. So it is given as minus
2700
kilojoule per mole. Per mole means this is the amount of energy released per
180 grams
per its
1 gram
molar mass of substance. What is its molar mass?
180.
180 grams. Okay. So but how much energy is required? 10,000. Okay. So for 10,000
How much?
kilojoules of energy is required. For this, how much is required? So use the unitary method, you can find this. Okay. 667 kilojoules, right? Yeah, grams here. Okay. So x will be 180
Into 10,000
by 2700. Okay, just do like this. Okay, next, Hess law. So what is this Hess law means? See, some reactions may take place in more than one step. Okay, whatever the way it is undergoing, whether a reaction taking place in one single step or in multiple step, the enthalpy change for that particular reaction will be same. Whether it may happens in single step or multiple step, the enthalpy change will be same. Okay. So for formation of CO2, it can happen in multiple steps or it can be done in single step. Like see, first method here we have C plus O2 gives rise to CO2, we are writing delta H. Okay. Second method, see, first it is forming carbon monoxide, again second step it is forming carbon dioxide. So here I can say delta H is equals to delta H1 plus
H2.
delta H2. So now following the same thing, just answer this question.
Which was A to D.
So a reaction is taking place from A to D, given as X as enthalpy change, and the same reaction taking in multiple steps. So tell me delta H2.
H2. X1 by X2.
So tell me this. Here I am saying delta H is X. This is X1. this is x delta H2 we need to find, this is x3. First option, yeah. See what to do, see the reactant of this reaction is the product of this reaction, so I can remove them here also, okay. So directly we are getting A to D, so now that is nothing but delta H final is equals, delta H this final is equals to A to B, B to C plus C to D. So I can say x1 plus delta H2 plus x3, and this delta H is how much they mentioned? X. So delta H2 will be
x minus x1 plus x3.
okay, simple. Next, so we'll study this second law of thermodynamics. 1 minute. Yeah, so we'll start. So till now we have discussed about enthalpy, like thermochemistry part. Now we will be discussing second law of thermodynamics. So what first law of thermodynamics says us? Tell me first. Energy of an isolated system remains constant. Okay, but second law says that entropy of an isolated system tends to infinity. It means it always keep on increasing. So how can we understand this? You take any naturally occurring process in the nature. So what happens during that process? Randomness of that particular process will be increases. For example, flowing of water. What happens? Flowing of water from high hilly region to ground. What happens? Falls. So what about the randomness of water here? Increasing. So any process you can take in the nature, so its randomness will be increases. So what is the term entropy here? It is nothing but the measure of disorderness or randomness of a particular system. Okay, so for a natural process, randomness increases, so entropy increases. So by combining first law and second law, what we can say? Whereas energy remains constant. So for an isolated system, entropy increases whereas its energy remains constant. So this is from both first law and second law. So entropy means measure of randomness, okay, and it is an extensive property. So what is an extensive property means? It is a mass dependent property, quantity dependent property, okay, and it is a state function. Okay, so now extensive and it is a state function. I am saying the exact value of entropy cannot be calculated, just we are calculating change in entropy. Okay, so this entropy change mathematically given as energy, like heat energy change divided by temperature, dq by T. Okay, this is the mathematical equation for what? Entropy. Okay, yeah. So next step. Now we need to calculate this entropy for different thermodynamic properties, processes. We will see that. Yeah. For example, what I am saying, delta S is equals to dq by T I am saying. So now I am asking you to calculate how you will do for isothermal process. So what is constant here? Temperature constant. So from first law of thermodynamics, what you can say, du equals to dq plus dw. Okay. So for isothermal process, what is constant here? U is temperature constant, u is also constant, du becomes 0. Therefore dq equals to minus dw I can say. So from these, dw is nothing but minus pdv. So I am saying isothermal reversible process. This is, what is that? Isothermal reversible. So now here dq, which process we are studying? Reversible now. So dq reversible equals to what I can say? Plus pdv dq reversible. So now what is entropy formula we have? ds equals to dq by T we require. So I can divide this equation with T, Therefore, here also I can divide with T. Okay, so dq by T means del S, entropy change. Okay, so we got this. So I can write del S reversible, and which process? Isothermal process will be equals to P by T dV we have. So from PV equals to RT, what I can write here? P by T is nothing but R by V we have. So here I can write R by V dV. Okay, so integrate this equation from S1 to S2 ds. Here upon integration, what will get? R 1 by V dV. 1 by x dx is what? V1 to V2. 1 by x dx is ln x. So from that we can get here R into ln V V2 minus V1. So I can write ln V2 by V1 from here. Okay, and here this will be del S by substituting upper limit, lower limits here. Okay, so this is for 1 mole. Okay, for n moles it will be nr ln V2 by V1. Okay, so you just remember these formulas, like isothermal work done process, how much it is on, like formula we have minus nRT ln V2 by V1. Okay, so this is nothing but what I told you, work done in isothermal process. So that is nothing but, see here, instead of writing minus nRT, I can write minus W equals to plus Q, like this. Okay, so now this Q by T is nothing but delta S. So just divide this equation with T. So here temperature is removed, you can have nR ln V2 by V1. So why I am saying this? Just to have that clarity. If you forgot this, you can get it from the work done formula also. Okay, right. So like this, if we calculate for different process, we have different formulas here. So for isothermal process, what we have seen? nR ln V2 by V1. For isochoric process, we have NCV ln T2 by T1. And isobaric process, we have NCP ln T2 by T1. Okay, so these are the important formulas. We will see the questions based on this. Okay, one question you can write. What is the entropy change? What is the entropy change? What is the entropy change when 1 mole of N2 gas undergoing isothermal expansion from 2 liters to 20 liters at 27 degrees Celsius. Simple formula substitution.
So
27.
I think with this.
So, okay, you can do now that one. So, similar questions are there in module, you can try that. If you have any doubts, you can ask me.